Hi guys, and welcome back to Introduction to Mechanical and Automotive Engineering. I'm your lecturer, Dr. Elizabeth Kyriakou, and this week we are looking at internal loads. So up until now we have been looking at only external loads acting on a system, but what are the implications of the loads internal to the structure? So let's take a look at internal loads. So if I have a beam, and we've been looking at beams for all the semester so far, and I know that at one end I'm going to have a pin joint, and on the other I'll have a roller joint, and we can call this B and this side A. So immediately I know that on a pin joint I'm going to have an AY and an AX component. And at my roller, I'm going to have just a vertical component. So I can apply a load, F, to my system. I need to be able to make sure that this system is in equilibrium first. So the first thing that we need to always do is find our reaction forces. So we'll find reaction forces. And we should always put an axis so we can identify which way is positive. So I can find my reaction forces. These forces, so AX, AY, BY and F, are all what we call external forces. So if I use method of sections that we did in structural analysis, and I can cut this beam at a point, let's just call that C, okay, and I'm taking a section. I'm now going to expose the two ends of this cut, and that's what we call our internal forces. So we're going to identify our internal forces. So I'm going to redraw this free body diagram and actually show the joint at C, or the section at C. So here we have A, and that's going to be C. And on this side, it's going to be the same thing. And here we have B. So I know from this free body diagram that I have AY and AX, and on this side I just have BY. So now I have exposed the beam where I have cut it at section C. So what's happening here? I'm going to have three internal loads, okay? I'm going to have a normal force. So N is going to be the normal force, and that is perpendicular to this surface, because it's a normal force. I'm also going to have a shear force, and I'm going to call that V. So I'm going to have a shear force. And I'm going to have a moment. That sounds very clear. Call that N. Okay, so I have three forces that are internal to this beam: a normal force, a shear force, and a moment. My shear force is parallel to the surface that I have cut. My normal force is perpendicular to the section that I have cut. So now if we take a look at the other side of this free body diagram, we need to be in equilibrium. So therefore, this has to be equal and opposite. So I'm going to have a normal force, a shear force. At this time my shear force has to go up because this shear force is going down, and they need to cancel out. And finally, the moment is going to go in the opposite direction. So this is actually my sign convention. So when you're cutting a beam, the direction of your normal, your shear force and your moment has to be in this layout. So this is my sign convention, and it's very, very important. So I think we should take a look at a quick problem and apply this to mechanics question. Okay, so if we take a look at this question here, it says we want to find the internal loads at C. So as soon as a question says I want to find the internal loads at a point, I know that I'm going to have to cut the beam, and the internal loads are the shear force, normal force, and the moment, the bending moment. Okay. So when we talk about bending moment, we're saying that if I have a beam here, and I have two ends, and there is a load, what's going to happen to this beam? It's going to bend. And we have, this is what we're talking about when we're talking about bending moment. So, let's just clean this off. So the first thing that we usually do with all our problems is we have to calculate our reaction forces. So we know that at A, we're going to have an AX, an AY, and a moment. I'm just going to try to do this question quickly and just focus on the shear forces, the normal force and the bending moment. So I'm going to let you calculate the reaction forces first. So this is similar to when we were doing method of sections, how we would just look at only one part of the problem. So I'm going to solve this, and the simplest way to solve this with a distributed load of a triangle is I'm going to look at this section of the triangle. So I'm going to analyse from B to C. I'm going to analyse the truss, or the beam, sorry, from B to C. And I'm going to draw a free body diagram of that. So here is my beam, and this is C where I've cut the beam, and B. And I have a distributed triangular load on that. So here is my triangle distributed load. and I have a distance of 2.4 meters. So what do I know? I know that at C I'm going to have 3 internal loads. So what are we going to have? We've got to keep our sign convention the right way. So we're going to have a normal force or a tension, a shear force, and a moment, a bending moment. So I have to calculate these 3 forces. But first, I have to sort out what I'm going to do with this distributed load. And a distributed load I need to turn into a concentrated force. So I don't actually know what the height here of my distributed load is. I know what it is at the end of the beam. It's 300 newtons per metre, but what is it here? How can I solve this? So I'm just going to draw the original triangle. So this is my beam from B, and this is A, so it's the original, and the distance of the whole beam is going to be 3.6 metres. And I know that this height here is 300 newtons on the metre. So I can do similar triangles. So similar triangles to calculate the height of this, because I know that the angles are the same. So here is my other triangle, and this is at point C, and here I have, is it 2.4 metres? And I need to find omega. So this is omega here. So I can just take the ratios now and say that 300 on 3.6 is going to equal omega on 2.4. So this is proportional triangles. So the ratio of the height and the length for one triangle has to be the same as the other, as the smaller triangle. So now I can solve for omega. So omega is going to be 200 Newton on the metre. So this is now, this here is 200 Newton on the metre, and this is my new distributed load. And what do I need to do to a distributed load? I need to convert it to a concentrated force. And we've done that 1,000 times, guys. So let me just clean this up, and we will take a look at solving the internal forces in this system. All right, so I'm going to redraw my free body diagram. Here's my free body diagram, and here is my beam at C and B. and I have a distributed load here, and I need to turn this into a concentrated force, okay? And I've already calculated this is 200 newtons on the meter, and now I need to calculate the concentrated force. So I know what my length is. My length is 2.4 meters. And how do I calculate the concentrated force? It's going to be the area equals half the base times the height. So I have half, the base is 2.4 meters, the height is 200 newtons on the meter. The meters cancel out, and I can calculate my internal load to be my distributed force to be 240 newtons. And where does that sit? That sits at 1/3 from the heavy side. Okay? So it's going to be 1/3 times 2.4 meters, and that is 240 newtons. So that's going to equal 0.8 meters. Okay, so let's redraw a free body diagram. I'm actually going to clean this up and draw it here. So if I redraw my free body diagram, I'm going to have, guys, I hope you realise how many free body diagrams I draw. Here is B, here is C, and I know that I have 240 newtons, and from C that is 0.8 meters. And what do I have at C? I have internal loads, and my three internal loads are tension, or the normal force, the shear force, and the bending moment. So I'm going to have the tension, the shear force, and this is all at C, and the bending moment at C. So let's draw in an axis here. And this part is actually very simple, guys. If I want to find, actually just let me clean this up. So tension is in the horizontal direction, it's in the x direction. So if I want to find tension, T, I can do some of the forces in the x direction has to equal 0. So what forces do I have in the x direction? Well, actually, I don't really have any. So here I have minus T, so therefore T equals 0. Okay. So then if I want to find, so that's my tension force, or the normal force. If I want to find the shear force now, to find the shear force, okay, I'm going to V, so it's VC. I'm going to say some of the forces in the y direction has to equal 0. So that's positive, VC is positive, minus 240 newtons. So therefore, VC is equal to 240 newtons. Alright. So now, the last thing I want to find is to find the bending moment MC, I can say that some of the moments around C has to equal, it's not going to equal, has to equal 0. So we're going to have, this is going in the negative direction, so we're going to have minus MC, and we have the moment from this force, so that's going to also go in the negative direction, and we'll have 240 times 0.8. So MC is going to equal minus 192 Newton meters, which means MC is going to be 192 Newton meters in this direction. So there we have the 3 internal forces at point C on this beam.